So hello and welcome for today's session. So today we're going to talk about the BJT. We'll work out a few examples on the BJT amplifier. So BJT working and its amplifier explanation that has been done in the previous tutorial, so that you can refer it there. So now let's take a few simple examples and see the transistor as an amplifier. So the first example which we look into here is that a transistor amplifier has voltage gain of 50, then what is the output voltage when input voltage is 100 millivolts? So this is the question. So here it is given that a transistor amplifier has a voltage gain, that is AV of 50. Well, you don't need a video, so my audio is quite enough. So video I have disabled it. Okay. So a transistor amplifier has a voltage gain of 50. What is the output voltage when the input voltage is 100 millivolts? So now in this case my AV here is that the AV is equal to, which is given as the 50, and the VB, which is equal to my 100 millivolts. So if this is a thing, then we know that from the formula from the previous tutorial we have seen that the gain is defined as the ratio of the output voltage by input voltage. So here the transistor amplifier, the output voltage is Vc and the input voltage in the common base configuration. We are talking about a common base configuration circuit here. So the input voltage is defined in terms of Vb. So now the output voltage is nothing but the product of the gain, voltage gain, with the input voltage. So that we will get this as, that is equal to 50 into 100 millivolts. So this will be equal to, say, 5 volts. So this is the answer for this. So let's take the another example here. Yeah. So if we talk about another example, so determine the voltage gain and the AC output voltage for the circuit. Assume that RE dash is equal to 500 ohms. So RE dash is nothing but the internal resistance across the emitter. So that is the RE dash. So this is our second example here. Okay, so circuit is given like this in a common base configuration. So emitter is grounded here. Then we have the AC source, and that is driven by a DC supply here. That is driven by the DC supply, and then here that this is VCC, this is RC, this is 1 kilo ohms, this is the V out which we are talking about. So here the V out is nothing but, we can call this as also VC here, and this is the RB, which is given of Okay, RB is not given here, and the voltage from this point to this point, it is given, this is as 50 millivolts, and this is VBB is not given here. So anyway, that is all not required. So here we have to determine the output gain and determine the output gain and the AC output voltage for the circuit. Mr. Chetan, my voice is audible, that is more than sufficient. You don't need a video here. Okay. Oh, okay. Screen video is not visible. Sorry for that. I didn't understood your question. Sorry, I apologize. I understood like you want to see the video. Okay, the screen you are talking about. So you should put clearly, sir, the screen is not visible, not the video. Okay. I apologize again. Okay, now is it visible? Sorry I forgot to share the screen. So you should be very particular when you are asking the question. It is not the video. Let me repeat. It is not the video. It is called as a screen sharing. Am I clear? Okay. So now the screen is visible. So let me revise quickly that the first example which I talked. So the transistor here, the first example which I talked, a transistor amplifier has a voltage gain of 50 volts. Then what is the output voltage when the input voltage is 100 millivolts? So it is very simple case. So AV is given, which is of 50, and VB is equal to 100 millivolts. So I'll just substitute this AV is equal to VC by VB. Then the VC, we can just calculate the product of the gain into the input voltage. So we will get this as equal to 5 volts. So that is the first example. So second example here it is given. So determine the voltage gain and the AC output voltage for the circuit. So here, so we have to assume that. Stuck. So we have to assume that the internal resistance, the internal resistance of the emitter is 500 ohms. So this is a circuit which is given. So now here we have to determine the output voltage here. So we'll take again the equation from the previous tutorial. We can write this. We have written this, that is VC by VB, and along with this we have also rewritten this equation as IE into RC by IE into RE dash. So it means we can also write this equation as RC by RE dash. So this is the RE dash. Then this is equal to if you substitute here, the RC value is given. So this is 1 kilo ohm, and the internal resistance of an emitter is given. So that is 500. So here, if we solve this, we will get the gain as equal to 20. The gain we will get here as 20 here. So now we have to calculate the output voltage. So the output voltage V out, which is equal to AV into how do we calculate? It is V out is nothing but our VC. So V out is nothing but VC itself. So don't get confused. So V out is equal to the input voltage, that is VB. So just substitute this 20 into it is 50 millivolts. So you calculate it, and then we will get this as equal to 1 volts. So these are the simple examples that you can work out. So similar kind of examples are there. Everywhere like gain is given, the current is given. Okay, so there is one more example with respect to current. So let me talk about that. Then we'll move on to the next topic. So let's take one more example here quickly. So third example is a change of 20 microvolts in base current results in a change of 2.5 milliamperes in collector current. Calculate the current gain. So here we have to calculate the current gain. So current gain is nothing but it is same as the voltage gain, but it is in terms of current, that is output current by input current. So it's a very simple example again here. So it is given the change in the 20 millivolts in the base current results in the change in the collector current of 2.5. So then that is AI is equal to, it is given as the output current is IC by IB here. So just substitute these values, that is 2.5 milliamperes by 20 milliamperes. So then this is equal to 125. So this is equal to 125, the gain and the current gain which you will get it. Okay, so this is how we will going to get it. So as a simple example, so I request you all to work out in a similar way. You can find it many similar examples on this. So we'll talk about the next topic now. The next topic which we're going to talk about is the BJT as a switch. So BJT as a switch. So now BJT or a transistor can be used as an amplifier, or it can be also used as a switch. So as I told in the last session that the BJT works in three regions. One is the active region, saturation region and cutoff region. For transistor to work in the active region, so it has just a minute, I'll draw the output characteristic graph so that it is very clear when I talk about these topics. So if you look into the output characteristic graph of common emitter configuration, then so this is my output voltage VCE, and this is the output current IC here. Then this is plotted for the different input current. So the different input current here, it is in terms of IB. So then we will get something like this here. Okay, so this is for different IB. Okay, and here it might be very small. This might be for very small IB. So then if I plot these, then it is something like this region. Let me change the color so that okay, and here we have something like this. Now this region, whatever you see here, so this might be for you say, okay, let me turn back the color black. So this might be an IB for say 10 microamperes. This might be an IB for 20 microamperes. This might be an IB for 30 microamperes, and so on. As you keep on increasing the IB, the input current, the output current also increases and gets saturated to higher values. So this floor bracket here, what I have written, so this is, we call it as an active region. So this is an active region, and this portion from yellow line to this is 0. So this we call it as the cutoff region. So this is the cutoff region, and this region is, we call it as the saturation region. So this you call it as a saturation region. Then this we call it as a saturation region, this we call it as cutoff region, and this we call it as an active region. So So now for the transistor to work as an amplifier, it has to be here in this region. It has to be in this region means that there is something called Q point. We have to fix the Q point somewhere within this region. It should not enter into the other two regions. This Q point has to be here. So we will not talk about how to fix this Q point because that comes under the DC biasing. That is way beyond out of the scope of your syllabus currently. So I'll just understand that there is something called Q point. So that Q point we have to fix it. If the Q point is within this region here, so then we say the transistor is in the active region. If the Q point is shifted somewhere here or here, then we say here the transistor is in saturation region and here the transistor is in cutoff region. So for the transistor to work as a switch, it has to be work between the two regions, that is the cutoff region as well as in the saturation region. So now we'll talk about, now you understood what is the saturation region and cutoff region. So I'll tell you how it will enter into saturation region and cutoff region. Now you all have seen the transistor configurations, the connections of a transistor here. So if I write a common emitter configuration circuit, then that is plus VCC into RC, then this if the so when do we enter into this cutoff region? So when we reverse bias both emitter base junction and the emitter base junction and the collector base junction, if you both reverse bias, then the transistor will be in the cutoff region. And if we forward bias both emitter base junction and the collector base junction, then the transistor will be in the saturated region. So now we have to switch between these two. So first what we'll do, we'll emitter base junction we will reverse bias. Reverse bias in the sense we will apply, it means it is zero voltage itself. So when the emitter base junction is reverse biased, then it means there is no current flowing here. So then IB is equal to 0, and then RC and IC, then the transistor is something like it is in the off state. So here we have an RC resistor, and now the transistor will be something like this. It will be in the off state. So this is our VCC here, and this is the RC resistor. So there is no current flowing from collector to emitter. It is open circuit. So in such case, what happens here? So you will get the voltage here which is equal to VCC, and which is approximately equal to VCE saturation. This voltage we call it as VCE saturation, which is equal to VCC when the input current is 0. And what is the output current that we will get? When the current doesn't flow from collector to emitter, then what happens? Then our IC current is also equal to 0. Input current is 0, output current is also 0. When input current is 0, the transistor remains to be in the off state. When the transistor is in off state, then there is no current that is flowing from collector to emitter. When there is no current flowing from emitter to collector, then what do we have? Here, if you measure the voltage across the RC, it is same as the VCC itself, so that we call it as the output voltage. So output voltage is VCE, which is approximately equal to VCC itself. So now let us write the other case. So this case what I have written here, so this is the cutoff region. So this is the cutoff case. So next I will write the saturation. So saturation, I will forward bias both emitter base junction and the collector base junction. So when I forward bias both the regions here, so then what happens, I have the base current here. It means the high base current is entering IB here. So this is RB, so this is RC, and this is VCC, the voltage, the DC voltage which we applied, and the current which is flowing here, so this is IC. So then the it looks like it is when the transistor is on, it is if you just look into like intuition or the analogy, if you see, then it is something like a switch which is closed. So when the switch is closed, the entire current from collector to emitter, it will flow. So now the VCC, now the current is flowing here, now this is my RC. If you measure the voltage here at this point, then this voltage VCE, when we measure it with respect to ground, this is equal to 0 volts because it is short circuited, because entire voltage from here it is shorted to ground. Then the current flows. So the current flow equation can be written in this way. If you apply the Kirchhoff's voltage law here, so if you apply the Kirchhoff's voltage law, then we will get the equation for current as, okay, let me write something like this. So we'll get minus VCC, then we have this is plus minus, so if I write here, this is NPN, so this is plus VC saturation, then it is plus IC into RC. So this is the equation which you will get, which is equal to 0. Now I have to equate this equation for the IC, the collector current. So this is equal to VCC minus VCE by RC. VCE by RC. So this is the final equation which we get. So yeah, so this is the final collector current equation which we are going to utilize in the saturation region. So in the cutoff region, what is the value of IC? In the cutoff region, the value of IC remains 0. In the saturation region, the value of IC is VCC minus VCE divided by RC. In the cutoff region, so VC is almost 0. So then we can write this is equal to VCC by RC in short. So we can also use this because VCE is equal to 0 because of ground concept. Okay. So now this is about the analysis. Now let us look into a few examples here with respect to this switching action. So here there is one example. So let me write that with respect to this. So in the circuit, below, so first one is that what is VCE when Vin is equal to 0 volts. This is first one, and the second question was supposed to be the second question here. And the second question is, what is the minimum value of IB is required to keep the BJT in saturation, given beta equals 200. Third, calculate the maximum value of RB when Vin is equal to 5 volts. So this is the given question here, and the circuit is, let me draw the circuit which is given here. Then we have the VCC equals 10 volts, and then RC is equal to 1 kilo ohms. So this is RC. So then this is RB. Then this is Vin. So this is a circuit given, so this is the VCC point here. So now what is the first question? When VCE, what is the VCE when Vin is equal to 0? So when Vin is equal to 0, what happens? The transistor will remain in the off state. When transistor is in the off state, so what is the voltage? So it is something like as an open switch. Just now we have discussed it is in the cutoff region. It is something like this. So when you measure the voltage here, that is VCE. So this VCE is approximately equal to what? VCC. So therefore, the solution for the first case is that so VCE is equal to VCC, so it means it is 10 ohms. Okay. So what is the next example here? What is the minimum value of IB required to keep the BJT in the saturation when the beta is equal to 200? So for this case, first we will calculate the IC saturation for the second case. So this is second we will talking about. This is the first one. So IC is given by IC saturation. So now it is in the saturation region. So let me write properly. When it is in saturation region, we have seen the equation is just VCC by RC. So use this equation VCC by RC here. So this will give the 10 milliamperes. Then the IB minimum, then IB minimum is equal to then IC saturation by beta DC. We have seen this in the introduction when we talked about the current amplification factor beta is equal to IC by IB. So we will use the same equation and rewrite in this fashion, that is IC by beta. So from this, if we substitute the values, that is 10 milliamperes divided by the beta is how much? 200. So if you substitute and simplify, then we will get here the answer as 10 milliamperes. Sorry, the answer in terms of current it is, so I'll get here the answer as 50 microamperes. So I'll get the answer as 50 microamperes. So this is solution for the second one. So if I talk about the third one here, so what's the question for third one? Let's see. So question for third one is to calculate the maximum value of RB when Vin is equal to 5 volts. So to find the maximum value of RB, we have to apply the voltage across this RB here. So if you apply the KVL across the input, so we have the voltage here, so this we call it as VBE. That voltage also we have to take into consideration, the voltage from base to emitter terminal. So if you apply the KVL here, so then if you just look into this here, so this Vn, this is for the saturation, so this is NP, so NP means this should be positive here, so this is Vin and this is VBE, so this will be positive, this will be negative. So if we apply the KVL here, so what we get is that, so this is my Vin, so then I'll get my KVL is minus Vin plus VB, that is the voltage across or you can just write VRB, voltage across the resistor RB, that is VRB plus VBE. So now I have to find this VRB, the voltage across B, then we can find the value of RB value. So then this is given as Vin minus VB. So VB during forward bias condition, it is just like a diode. When the diode is forward bias, what is the voltage drop across the diode? It is 0.7 volts for silicon. So same thing we will consider here also. So then this is nothing but we can write here as the input voltage is 5 volts minus 0.7. So we will get here the voltage, this is equal to 4.3 volts. So we'll get the voltage as 4.3 volts here. So then this is the value I'll get. So then with the help of the Ohm's law I can write, so RB is equal to VRB by IB. So So IB we have, that is 50 microamperes, and now we got BRB is 4.3, so divide by, so that is 50 microamperes. So this is equal to that 86 kilo ohms. So this is what uh, we will get here, RB, and here the answer, this is 50 microamperes, and the first one, it is, the answer is this. So I hope you understood this example. So similarly you can work out the examples which will be given here. So let us take one more example. So let me try the another example for this case, second example here. So the question is, what is the minimum value of IB required to saturate the transistor in the figure below if beta value is equal to 125 and VCE is equal to 0.2 volts. Again, it's a very simple example that you can solve it. So here again the circuit is given like this with the values. So this is resistor, the VCC value here it is given as VCC is equal to 10 volts. So RC is given as 1 kilo ohm, and this is the RB value here. So then VN, okay, so this is an NPN transistor RB. So now what is given here? So what is the minimum value of IB required to saturate the transistor in the figure below? So if beta is equal to 125 and VC is equal to 0.2 volts, okay, yeah, so beta is given, so what is the minimum value of IB? So we will first look into the saturation region here. So what is given here is that the VC is equal to, this is not just VC, this is VC saturation, means it when the transistor enters into saturation region, so it has a 0.2 volts. So then we will calculate the IC saturation value here first. So IC saturation we will not use in this case, that is VCC by RC, because that is a simplified version. Here since the VC value is given, we have to use that. So now it is VCC minus VCE saturation by RC. So now we are going to substitute the values for this. So this is 10 minus 0.2 here, divide by, it is how much, 1 kilo ohm. So I will get this current as 1.8 milliamperes. So 1.8 milliamperes. Okay. So after this, then I'll calculate the IB minimum. Then IB minimum is equal to the IC saturation by beta DC. IC saturation by beta DC here. So then this is nothing but, so this is equal to the 9.8 milliamperes by beta DC is equal to 125. So then, which is equal to 78.4 microamperes. So when that is what we got here. So we got the IB requirement at the saturation. So now, uh, okay, here the question continues. If you look into the question here, so the question continues to be also find the maximum value of RB required when Vin is equal to 8 volts, and Vin is equal to 8 volts. So now we have to also find what is the maximum value of RB. Let me put this question a little above, it is not visible. Yes. So we have to find the maximum value of RB when Vin is equal to 8 volts. So for that, what we will do is that we take the same input equation here. We have seen in the previous example that VRB is equal to, that is Vin minus VBE. So that is equal to VBE, which is equal to, so here it is nothing but 8 minus, so it is 0.7. So 8 minus 0.7 we will get here as 7.3 volts. So then the RB we can find here as simple. So RB is equal to, this is VRB by the IB saturation. So this is IB saturation, or IB minimum also we can write, the minimum current required to make the transistor enter into saturation. So this is 7.3 volts by, this is 78.4 microamperes, which is equal to 93.11 kilo ohms. So that's it, this example. So we have found the value of RB, we have found the IB. So that was that is it. It was asked to find. So we'll wind up for today, and 2 more applications of transistor of glowing LEDs we'll talk about in the next session. So thank you.